I didn't record this morning. So I got to record this now. Make sure it's recording. Is it going? No data. No data. Excellent. All right, ladies and gentlemen, here we go. Here we go. Chapter 10. Chapter 10. Estimating population means. So we estimated population proportions in chapter 8. Now we're doing population means. And again, the concept is the same. There are two differences. Okay? Two differences. So you know the formula already. This is the formula that's written in words, right? That's the formula that's written in words. You guys know from chapter 8. At least I hope you do. The statistic was p hat. The critical value was z. And we put a star there or we didn't, and I didn't really care if you did or if you didn't. And then the standard error of the statistic was the square root of p hat, 1 minus p hat over n. Okay with all that, good? So that was from chapter 8. Don't forget that. Don't forget that, but that was chapter 8. Okay? Now what we're going to be doing instead of proportions, we're going to be dealing with means. And so when I deal with means, that's going to be x bar. And this is the first change I got to talk about. The critical value will not be z. We're changing the critical value. We're changing the critical value to t's. And then the standard deviation of the sample is this one. We'll talk about that as we proceed on. This is on your formula sheet. This is not new. It's kind of new. You guys are used to seeing that. Okay? So here we go. Let's talk. Click, 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 click. Don't use this. Don't do this. All right. So big picture here, guys. Why are we doing a confidence interval? Because we don't know the population average. Fair enough? That's why we do a confidence interval, because I don't know the population average. Well, now I'm going to go way back in your old memory banks. Way back, right? That is the mean of the population. That is the mean of the sample. We have a standard deviation of the sample, and we have a standard deviation of a population. Okay with that, right? Again, notation you guys should know. We got to make sure we understand it, right? Well, here's the big key with this. In order to find this, I have to know this. In order to find the population standard deviation, I have to know the population mean. If I don't know the population mean, which is why we're doing confidence intervals, it's impossible for me to find that. Fair enough? So what do we use, or what can we use? Well, we know we're going to be using x bar to estimate this. And we know that these two values are probably different because they're sampling variability, right? We got a population, we got a sample, they're probably not the same thing. Well, not only do we have a sample mean, but we also have a sample standard deviation. And with the sample standard deviation, we probably know it's not the same as the population standard deviation. Good. So here's the issue with means compared to proportions. Because in proportions, all we needed was the p hat to estimate p. Because over here, we had the square root of p hat, 1 minus p hat, n, and this was p, 1 minus p over n, right? I only had to estimate one thing, p hat to p. Now I've got to estimate x bar to mu, but I also have to estimate s to sigma. So because I'm estimating two things, we got an issue. I need more wiggle room. Good enough with all this? We don't know the true value of mu. And if I don't know the true value of mu, there's no way for me to calculate population standard deviation or sigma. I can't. So because I don't have sigma, we're going to use the only thing we can use, which is the sample standard deviation. By using S, it gives me an issue that we're going to have to deal with. And so here's what they're going to want us to do. This goes through a whole problem and a whole applet of showing why. Get rid of it. You can see it if you want to, but yeah. Here's the problem with using Z. Here's the problem with using Z. Since we don't know the population mean, I don't know the population standard deviation. And if I don't know the population standard deviation, I'm having to estimate two parameters. I'm having to estimate two of them. I'm having to estimate mean and the standard deviation from two samples. Okay with that? So I'm introducing more variability because I got the variability from the mean and I got the variability from the standard deviation. So we got more variability when I'm combining all that together. Thus, the distributions for means follows a t distribution, not a z. So anytime we're dealing with means, we're no longer dealing with z's, we are dealing with t's. And that's the biggest difference between proportions and means. And guess what? In chapter 11, we're no longer going to have z-scores. We're going to have t-scores. Okay? So, why do we use t's instead of z's? Because I'm having to estimate two things. Do you need to know why we're using t's instead of z's? There probably is going to be a multiple choice question on that. Not a big deal. But if you don't use z's, that's a big deal. Excuse me. If you don't use t's, that's a big deal. You're going to have errors, big loss of points that way. Everybody okay? T's, not z's. So let's talk the difference between a t distribution and a z distribution. There's not a whole lot of difference, but we of course do need to talk about differences. The t distribution is still bell-shaped. It's still bell-shaped. It's still centered at 0. Okay, it's still centered at 0. It's still bell-shaped. So, not a whole lot of difference there. Not a whole lot of difference there. T distributions are wider because they have more variability. I'm having to estimate two of those things, so I need some wiggle room to help me. So because I'm estimating mu and sigma, I need a different number to help me make sure I help capture the true mean. So they're more spread out. If they're more spread out, what? They're also shorter, right? Because as I spread things out, they have to have shorter because the area underneath the curve is still going to be 1. The area underneath the curve is still going to be 1. T distributions are not constant like z's. Z's are z's. If you're 1 standard deviation away, you're 68%. If you're 2, you're 95. If you're 3, you're 99.7. T's change. T's change. They're going to be distinguished by what we're going to call degrees of freedom, or DF. DF is going to determine how wide that thing is. We'll talk about it in a second, but DF changes the width of those things. If it changes the width, it changes the height. If you squeeze it in, it goes taller. If you open it up, it goes shorter. They're all centered at 0. Okay with that. DF, degrees of freedom. DF, degrees of freedom. We'll talk about it in a couple more slides. As the degrees of freedom increases, those T distributions become more narrow, looking more like a Z distribution. As the degrees of freedom increases, those things become more narrow. Well, that's kind of nice because it kind of goes along with what you already know about sample sizes, right? As it increases sample sizes, the sampling distribution spread starts decreasing. And eventually, if you get a big enough degree of freedom, the T will look like a Z. Hit me. No. Z is the max it could possibly be. Yep, a T distribution will never be smaller than a Z. Z is as small as you can possibly get. Good question. Multiple choice question. What's the difference between T's and Z's? Or which of the following does not follow a T distribution? Which of the following is wider? There's several questions about T distributions on your test. Okay? T's are wider. If they're wider, they're shorter. T's change. As degrees of freedom increases, this thing decreases. It does have a limit on the max. Like at some point, it can't become any wider. And it can't become any narrower. We just have the wiggle room between it. Okay, some of y'all are writing some of that down. Anything different about it? You need to know T's and Z's. Hit me.
Based on the question or based on like just what you want to find out?
It will be based on the question. I'll show you. It's a hard formula. Luckily, our calculator does it for us. Everybody okay with this? T's and Z's. If you know that difference, 85% of the way done with this lesson. You just know you got to use T's instead of Z's. Proportions, use Z's. Means, use T's. Okay? Clicky, click, click. Just to kind of give you a visual, this solid pink line, you probably can't see it, is the Z. It's the tallest one up here. It's the one with the least area in the tails. It's a little bit narrower. The blue dotted is 9 degrees of freedom. The red dashed is 2 degrees of freedom. So it's the shortest and widest. 9 degrees of freedom is closer to a Z. Z, of course, is the narrowest. Okay, so there's not much difference. There's not a whole lot of difference in this tail area. So we're talking minimal numbers, but it's enough to make a difference. In statistics, we want to be as accurate as possible. And so that little bit changes our stuff. Everybody good? Questions? Huge, big deal. Okay, let's talk about this degrees of freedom. It's a difficult formula. It's not on your formula sheet. So, I mean, this is part of the differences. That's part of the T's. First thing you got to know about degrees of freedom is you got to know the sample size. Luckily, most of the time we do. Most of the time they tell us the sample size. So we got to know the sample size. Everybody established that. Got to know the sample size. A lot of you cats, unfortunately, going to have to turn on your calculators because we don't do math anymore. Some of you guys are good enough mathematically. You may not have to turn on your calculator. So we got our calculator on. You're going to enter that sample size in your calculator. 276, 84, 35, whatever it is. You guys are seeing all kinds of different sample sizes. After that, you might have to hit that minus symbol. Minus. Don't hit the negative. That'll give you an error. Minus. I don't think you need to put parentheses, but we're going to type in a 1. 1. And you're going to hit enter. And that's the degrees of freedom. It's not hard at all. It's not on your formula sheet, but DF is n minus 1. I don't think anybody needs their calculator for that. I don't think you actually need to show AP that DF equals 85 minus 1 equals 84. I think you're perfectly fine just saying DF equals 4, 84, whatever it is. Y'all okay with that? DF. You more than likely need to tell AP what it is. DF equals. You more than likely need to tell it. And I told first hour this morning, 0 hour this morning, I said, if they ask specifically for the DF, you probably want to do 84 minus 1. But if they don't ask specifically for it and you're just giving it, I don't think you need to show the subtraction. Y'all okay with all that? Okay, n minus 1, n minus 1, which kind of goes nicely because it goes along with the sample size. And what have we learned about the sample size? As the sample size increases, it decreases things. And as DF increases, that must mean the sample size increased. Y'all okay with all that stuff? So we can just kind of tie all that in together. Why do they subtract 1? I got no clue. Somebody a whole lot smarter than me decided they need to subtract 1. So the max DF could be, I guess, would be 0, but that would be a sample of size 1, which really doesn't tell me much of anything. And if DF happens to be 200,000, that might as well be a Z. Good enough? Click. Do not need to show the calculations. All right, now finding T. That's important too because you will be asked, what is the T star score? Just like you guys were asked, what is the Z star score? But you had those memorized, or at least for 95, you knew it was 1.96. And for 90, it was 1.645. And for 99, it was 2.576. And if you didn't have those memorized, hopefully you know how to find those. These are different because they're not the same for 95 because it's going to be determined by the DF. Okay with all that? So you got to know how to find these. And you're going to find it one of 3 ways. Table, calculator, Desmos. And I'll be honest with you, this might be one of the few times I actually use the table and I don't use Desmos. Well, I don't know how to use Desmos. I do. The calculator hurts you sometimes with this. So let's talk about the calculator portion of it. Let's talk about finding this, okay? I got a 95% confidence interval. 95 with a sample of size 12. Y'all okay? So 95% DF equals 11. Remember that those two help determine what my width is going to be. Z, that was 1.96. T's, it's going to be a little bit wider than 1.96. This DF is going to determine it. So if you wanted to, you could go to the table. Now you guys haven't seen the T tables yet. Formula sheet 1, formula sheet first page, formula sheet second page, negative Z's, positive Z's, and then there are T's. Okay, they're on your formula sheets, and I'll give you one if you want one for the test, right? Now's about the time where I'll start giving you the entire formula sheet. On the T distribution, guys, at the bottom, you'll see 95%. 96%, 98%, 99%, 90%. Okay with that? And then over here are your degrees of freedom. And so I would go up to 11 and go over to that 95%, which was this one, 2.201. 2.201. Good enough? That's how you find it on the table. Notice, hey, looky here now. Look at 95%. If I go to infinity, there's 1.96. So infinity is actually the z-score. Okay? Infinity is the z-score. So that's how you use your table. Calculator. Calculator. Be careful if you're going to use your calculator. Be careful. You might turn it on before you come to class. There. Okay. Second, distributions. Distributions, it's a T distribution. We have a normal distribution. Normal PDF we don't ever use. Normal CDF we do. Inverse norm we do. Inverse norm finds the z-score. You do center. There's inverse T. inverse T. There's a TPDF you'll never ever use. TCDF you might use, but you're not going to use that till chapter 11. But notice that I don't have left, right, center. Notice it's not asking me anything else. It's just doing inverse T. Does yours ask questions? I got mine turned off. I must have done something. So it says area. Area. Okay. So this is where students mess up because the area is not 0.95. That's the middle. This calculator only goes to the left. So if you got 0.95, that's 0.05 left over, which is 0.025. 95, 5 left over, 0.025. Okay? Be careful if you're going to use TI to do that. And then you got to put your DF. DF was 11. And that's going to give me the negative one. That's okay. It gives me the negative one. That's fine. But that's that same 2.201. Okay with that? I don't know what Desmos does. Go ahead. You're fine. Desmos may give you that center button. However, you have got a pretty big nerd as a teacher who happened to write a stupid program called CritVal. Oh yeah, I remember this. And we run it. And 2 chapters ago, we ran it for number 1 because it was all proportions. Now we're going to run it for means. And it's going to ask for the confidence level, which is 95 or 0.95. Your nerd teacher doesn't care which one you put in. Enter DF. N minus 1 if it's means, N minus 2 if it's slopes. Slopes are not till chapter 12. 11. Yay? Whoop, there it is. Rounded, 2.201. The T score is, yay? Or Desmos. Yes, sir. I took 95, I took 100 minus 95 and divided it by 2. To actually, it's integrating, but the curve changes. The area curves between the 2 values. Yeah, so you gotta find the area that, you gotta figure out what the curve's equation is and then find the area between those 2 values. Sorry. Calculus. Y'all okay? I don't care. I promise you on your multiple choice, you're going to have to give me the T critical value. On your homework tonight, you're going to have to give me the T critical value. Desmos, table, TI, don't care. Desmos may work just fine. I don't know. You guys will look at Desmos and you can find it too. T distributions. It may have a center button. If it has center, you need to do 0.95 and it gives it to you because it's going to give you the left and the right. Everybody okay? Hit enter. Created by me because he loves you and I don't get any royalties. So you owe me some Cheez-Its. I spent my time to write that whopping 8-step program. I'm just kidding. Hit enter. Done. Clear. Yay. Back to normal. Don't ask me if that program's legal or not, because I don't know. And if you don't want to know the answer to something, you don't ask the question. So I have never asked anybody that question. I don't think it's illegal, but I don't know if it's legal. My NumWorks calculator, I can do the 95. Makes me think that you can do on Desmos, you can do 95. And if you can do that on those calculators, why can't you do it on ours? Because, never mind. There it is, 2.201 if you're using the table. Seriously, the table might be the easiest still. Just understand that the table, I do want you to know this, the table does skip some values. Okay, 50, 60, 70, 80, 90, 95, 96, 98. It skips 97. 98, 99, 99.5, 99.8, 99.9. Okay, and then also it skips some DS. 1, 2, 3, 4, 5, 30, 40, 50, 60, 80, 100. And it's because these values, this is 1.303 and 1.299. There's not a whole lot of difference between them. Okay with all that stuff? So just recognize that if you're using a table, you may not find the exact answer, but you're going to get close enough where you'll get your points. Okay with all that? Good. Anything about the T critical values? That's really, I mean, I told you there's two differences, and that's 90% of the differences, maybe more than that. DF is new, but DF goes with T's, so everybody good? Anything about it? T's, T's, T's. Coffees. Click. Inverse T if you're using your calculator, just be careful about the tail. If you use Coach Mayer's problem, or you're good, because he calculated the tail for you. I don't even think the old 83s have an inverse T. So you'll either have to use Desmos or the table, because the old 83s don't even do an inverse T. Okay with that? I think he's the only one with one. Here's a 90% with 48. So the DF is 47. Okay? So you would go to 90%. You don't see 47. You would just go up until 40. Don't round it down to 50. Don't round it down to 50. That's too big. So round it back to 1.684. This is 1.676. And if you wanted to somewhat do a ratio, but don't. Now, it's going to be a different answer than your calculator, but it's going to be okay. Yes, ma'am. Always not. Yeah, because it's subtracting 1. And if you subtract 1, you're just going to keep subtracting 1 until you get there. Everybody okay with all that? Beautiful. Beautiful. Oh, this was 1.684. And here, oh, that's what that was. That's the exact same value. 1.6, no, it's not. 1.678. That was 84, so it's 0.005 off. All right, conditions. I got to give you the conditions for this. I don't have to. You guys are going to give them to me. All right, what's one of the conditions? Large counts. What's the other one? 10%, and the other one is? Random. Thank you. You should get yours first. You were the females. Females first. Okay? Here's the difference. Here's difference number 2. Okay, so random is not different. It's got to be a random sample. It's got to be representative of the population. We're still going to do 10% unless it's volunteers and we're using an experiment. It's the large counts or the normal. That changes. But now, guys, you're kind of lucky because that's changed for all of them. The large counts has changed for all of them. In 8.2, it was n times p hat. N times 1 minus p hat. 8.3 was n times p hat 1. N1 p hat 1. N2 p hat 2. N2 1 minus p hat 2. 9.2 n times p. N times 1 minus p. 9.3 n times p hat sub c. Holy cow, right? 4 different ones. We got a different one now. And guess what? You don't have a P, so you're not going to use N times P. Fair enough? We don't have a P. So this one's completely different. You might have to think back to chapter 7. In chapter 7, that's where we did sampling distributions. And we did, what was that stupid theorem? Central limit theorem? Something about 30. We want our sample size to be larger than 30. Uh-oh, might want to turn the pencil on. That's all you have to do for this one. N has to be greater than 30. It could be equal to, that's fine. Yep. Okay with that? Here's the little caveat to this. What if n's not greater than 30? Well, I hope the population is normal. Y'all remember this? If the population is normal, what about each one of my sampling distributions? Normal, right? I don't care what the sample size is if the population is normal. And that happens every once in a while, especially on problems that I forgot to make n big enough. And when I forgot to make n big enough, then I threw on there, assume the population is normally distributed. Good enough with that? And then there's one other instance. And this is the one AP likes to do a lot of. Instead of telling you what the sample size is, instead of telling you that the population is normal, they give you the data. They give you the data. They couldn't give you the data with proportions, right? Yes, 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 no, yes, no, yes, no. They're not going to do that in proportions. You're either in that category or you're not. Now they can give you the data, your test scores, 82, 83, 82, 85, 97, 0. Forgot to take it. Okay with all that? So they can give you the data. Well, if they give you the data, what do we hope? Hope they give me 30. Hope they give me 30 and then I don't care. If they don't give me 30, which they're not because 30 is a lot of data, then you're going to have to graph it. One of those three will happen. One of those three will happen. It's possible that two, but you only got to show one of them. We hope the sample size is bigger than 30. And you guys think back, how many times you think our sample size has been less than 30? Very few times. Very few times. It doesn't take much to get a sample of size 30. If it's not 30, we like for that population to be normal. What if it's over 30 and the population is normal? Good, you fit it twice. Who cares? You can say it either way. The population is approximately normal. Therefore, the sample is. Or n is greater than 30, we're good to go. And if they don't do either one of those, they got to give you the data and you're going to have to graph it. And I always graph a box and whisker. Because a box plot. Box plot. That's the easiest one to draw on your paper. That's the easiest one to draw on your paper. You don't really want to do a dot plot because that takes a lot of dots. You really don't want to do a stem and leaf plot because they're harder to draw. You really don't want to do a histogram because they're harder to draw. Box plots are the easiest to draw. And you got to draw it on your paper to prove you did it. Good? That's what all this says. I'm going to try to prove large counts for this example that I have up here on the board. Y'all have that one? Is that right? Same one? Okay. What do we like about it? Do we like that shape? Yes, no, maybe? It's got some gaps in it, but it starts low, it goes high, it starts low. But how many students do I have? So I don't even care what that stupid graph looks like. Don't even care. Yes, approx norm n equals 50 greater than 30. You don't have to write this part. You don't have to, this you do. That proves the large counts. That shows large counts. Anybody, you're all okay? Good? Next one. Yes, the sample size is large. 50 is greater than 30. 20. How much does it force it? It doesn't say anything about the population. So I don't know about the population. My size is not big enough. I got to look at that stupid stem and leaf plot. And that stupid stem and leaf plot is what? Strongly skewed. Not only is it strongly skewed, it's possible outliers on there. Okay with all that stuff? I don't think I can use that on this data. I don't think I can do this data. And AP asked, what would you have to do? I need to get 10 more dudes. I need 10 more dudes. Good enough with all that? Skewed which way? Left. Skewed to the lower numbers, if you forget that. Skewed to the lower numbers. Skewed left, skewed negatively. Don't forget that stuff. Don't be a knucklehead and say skewed up.
Somebody actually said that?
No, but if you do, then you're skewed up. Oh, thanks. Shut up. I know what you're thinking. Go ahead. You keep thinking it. You're still thinking it. Dork. Takes one to know one. So weird. What about this one? Bad? Only 20? Y'all okay with that? We are. I'll just tell you we are. It is skewed very slightly to the right. It's only a box plot. It's not strongly skewed. It does not have outliers. We're okay with that. We're okay with that. Most of the time, it's going to be absolutely obvious. It's going to be really obvious that you can't do it. Y'all okay? Good? It's going to be really obvious. They say this, the box plot is only moderately skewed. There's no outliers. We're okay with that. We're okay with that. Again, if I was doing this, I would have spent a little bit more time and gotten 10 more dudes. And then I wouldn't have to worry about it. And in fact, 20, if you guys think back to those things we did, 20 get me approximately normal most of the time. Click. If an AP question asks you to construct and interpret, that's the full-blown deal, right? You better give me a method. What's your method this time? One samp. Please don't put prop. Okay, don't put prop because this is not props. One samp mean t, and don't put test. This is an interval. That's your method. That's about as short as you can write it. Or you can write the formula. Gotten away from the formula. I think this is a better idea. You got to have the method. You got to have the conditions. There's 3 of those bad boys. You got to have some type of calculations, right? And in the calculations, what I end up doing is giving you what X bar is. I will give you what S is. I will ask for the DF. I'll put that down there. Are you required to? I don't know. It's good to. You just want to put down as much as you can. And if you're not sure, don't put it. You don't have to put the T critical value. And I recommend not putting it. Because if you put a T critical value that actually does not work with your interval, you're going to get dinged. You follow what I mean? If you calculated a T critical value and then you use your calculator to calculate the interval, it may have used a different T critical value. So I recommend not putting it. But then we got to have the interval. Got to have the interval. Okay? And then our conclusion, we are 95% confident that the interval above calculates the true mean. Blankety blank, 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 blank. Good enough? If you put proportions, yeah, you're going to get dinged. The sample, yeah, you're going to get dinged. Okay? But all this other stuff you already know. The biggest difference, T's instead of Z's. With T's comes DFs. You got to compare T's and Z's. And then the other one is the large counts proof. It's different for means than it is for proportions. We need n times p to be greater than 10 over there, and over here we just need n to be greater than 30. Yes, no, maybe. I don't know how much. I don't think you need to write any of that stuff down. I mean, you guys are probably pretty good at that by now. Y'all want to look at this? I'm not going to do the whole thing. I'm trusting you guys. In chapter 8, we learned about 73% of Americans claim to have read a book in the past 12 months. This was based on a random sample of 1520 American adults. Boy, that's pretty nice. The same study also reported that the average number, not proportions, of books read by members of the sample, including those who read 0. Here, looky here, they gave me X bar. And they gave me the standard deviation. They typically give you those values. They typically give you those values. And then it says construct and interpret. We got a random sample of 15, 20 adults. 15, 20 is less than 10% of all adults. 15, 20 is a whole lot bigger than 30. We're good with my conditions. We're going to do a one samp mean T int. X bar is this. Standard deviation is this. DF is 1519. And then I'm going to my calculator to calculate this thing. Let me show you that. Okay, let me show you that. Calculator. Stat tests. It's not a test. 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 Don't use Z interval. Let me show you. It asks for sigma. I don't know sigma, so don't use it. Go over here. T interval. T interval. It doesn't say one samp. It doesn't say means. You have to write that down. Enter. Now, here's where you're going to have to decide. Do you have the data or do you have the stats? This particular question, we have the stats. We have the stats. So we go over there to stats. We hit enter, and it asked me for X bar. And X bar was, I forgot, was it 12 or something? And then it asked for the standard deviation, which 18? Really? And there were what, 1520 or 1250 or 1520? I'm dyslexic. 95 or 90? Good enough with all that? Just plug and chug. Enter. Poof. There's your interval. There's X bar. There's S of X. There's N. Doesn't give me DF, of course. But I don't think it takes a whole lot to put DF is equal to 1519. What if I don't put DF? I don't know. It helps. Does it hurt? I don't think so. But, yep.
Will there be a question where they ask you, or they give you just the mean and not the standard deviation?
Nope. Nope. They'll give them both. That was chapter 1. No, that wasn't chapter 1. It's chapter 2, right? Where we talked about the mean, find the standard deviation. They're not going to ask you to find that because that's calculator work. They're going to give you that information. And then what? We are 95% confident that the interval from 11.09 to 12.91 captures the true, oh, I better not say the word proportion, because if I say the word proportion, Coach Mary's going to slap me. The true mean number of books read by whoever the heck this was, adults. Y'all good? Questions? Go back through the slides if you need to. You can bet your bottom dollar on the test there's going to be a question just like that, right? Very, very similar. Construct and interpret. Construct and interpret. Now, I don't know if it's one sample or I don't know if it's two samples. One sample T interval for mu, the true mean number of books you read by, yada, da, da, da. Do I need to put all that stuff? Doesn't hurt. If you don't, probably okay. Random sample, 15 or 10% normal large counts. Check, check, check. There's X bar. There's the standard deviation. That's with the table. I don't use the table. You don't have to put the T critical value. They need the interval. You don't have to put all this stuff. You can. It's not wrong. There it is. We are 95% confident. Yay? Let me go quickly. Oh, here says, it says this. Does your interval provide convincing evidence that the 2016 mean is different than 14 books? Ooh. Does it give me evidence that it's different than 14? Yeah. Yep. Don't say I have evidence that it's less than 14. Just say I got evidence that it's not 14. Because 14 is not in my interval. Yes, because 14 is not in the confidence interval, it's not a plausible value for the mean number of books. Just don't mention that we think it's less. Even though it looks like it's less, don't. Don't, because we did a two-tailed test. And we really don't know if it's this tail or this tail, although we do, but that's just one of those things like accepting the null. Everybody okay with that? Good? Nothing real new here. This one here, this one I want you to show you. I'm not going to do it again either, but same type deal, except what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. And they only gave me 20 data points. Okay? So what you're going to have to do is put that in your calculator. I always put it in L1. Put it in L1. Remember stat edit, put it in L1. Okay? And then once you put it into L1, you go to your calculator, stat edit, okay? Put it in L1, that's not the data, but I'm not putting it in there. Then once you go to stat, tests, and do a tint, you don't have stats anymore, you got the data. Okay, you got the data. Comes from L1. If you don't put it in L1, change it to L2, whatever. Frequency's 1, how often does it occur? Level is, I think this one's 90, 95, it doesn't really matter, right? Then calculate. And when you calculate it, guys, it gives you the mean and the standard deviation. And so just put those numbers down. X bar equals, S of X equals, N equals 10, DF equals 9. There's the interval. Y'all okay with that? But don't forget, you got your conditions. We got a random sample of 20. 20 is less than 10%. 20 is not larger than 30. The population was not normal, so you need to graph it. And you got to graph it on your paper. So second, I know this has been a while ago, second y equals, turn the plot on, turn it on. I do a modified box. That way it shows the outliers. L1, graph it. You probably won't see it. Zoom 9 stat. There it is. Holy, oops. I wouldn't use that data because it has a outlier. That's not the data though, right? I just made up that data. I don't even know where that data came from. Good enough, y'all okay? Let me kind of go through their slide real quick. I don't want to go too fast, but I don't want to bore you. I hope I'm not hurting you guys by not going through this step by step. I think I am on some of you guys. But one samp T, int, random, 10%. Notice that they did a dot plot. I would not do a dot plot. That would take too long to draw. You have to draw it though, guys. You have to prove to the grader that you did it. And the only way to prove it is to put it on your paper. Doesn't have to be beautiful. Sketch. Sketch. Just prove it. If there's a longer tail here, put a longer tail. If it's shorter here, put it shorter. Here's X bar, there's the standard deviation, there's DF, there's the interval. We are 90% confident that the above interval captures the true mean. I forgot what this was. Batch of video terminals produced that day. It's not enough to make the graph on your calculator. You must draw it. Sketch. Sketch it. The same thing happens as what you learned 2 chapters ago. If you increase the level 90 to 99, it's going to increase the interval. Okay? It's going to increase the interval. The margin of error decreases as the sample size increases. As my sample size increases, my margin of error decreases because my variability becomes less. All that stuff is still the same. The margin of error is proportional. 1 over the square root of n. I forgot, I don't have the square root button in there. It's proportional, right? So if I quadruple the size, it's going to cut my margin of error in half. Okay, that still applies. That still applies. The margin of error will be larger for higher confidence levels. We already talked about that one. The margin of error doesn't account for bias. Now remember that. If it's biased, that's my sample. My result's still going to be biased. It's still biased. It's the method I used over here has nothing to do with any of the calculations. I can't fix bias without fixing my question. All right, big picture. I hope you can find the critical values. You'll have some homework questions to be able to find those critical values. I hope that you can state and check the conditions. And I hope you can construct and interpret a confidence interval. Yippee, yippee, yo. Thursday's going to be what? The difference between 2. And then I'm going to have a vote out there if you guys want to take a test on Tuesday, or if you want to do 11-1 on Tuesday, do 11-2 on Thursday, review a day on that Friday, and then you'll take it the next Tuesday. Kind of okay with all that? Let me hit stop. Arrows, arrows. Homework should be posted, ladies and gentlemen.